What if this was a negative? This wasn't a positive.
All right, welcome back, everyone.
It'd be the same amount of
Welcome back.
Look at number 13.
So, in discussion, we started doing.
From the fourth.
Can I have your attention?
Number 5.
Everybody? All right, let's settle down and. Okay, so in discussion, we started doing. Well, we started last Thursday doing Gauss's law.
That means force is still the same.
Ready? Okay, so we started doing Gauss's law, and today I'm going to continue on that. And we will continue during discussion and even next Monday, or if you're in my class next Monday, if you're in the one tomorrow and Thursday for discussion, that's what we will do mostly.
It would be the same.
So we're going to learn how to use Gauss's law and how to apply it, and yeah, take it from there. So. Gauss's law, let's write it down. It says that electric flux with symbol phi E. Often I would just write phi if it's clear from the context that we're talking about the flux, electric flux. The reason that we say E, because in a little bit we'll talk about magnetic flux. We'll have flux due to magnetic field. So that's that. It says this electric flux through a closed surface, E dot dA, over a closed surface, that's what the circle means, is equal to the charge enclosed within that surface, Qn, divided by epsilon naught. That's what it says. Gauss's law is always true, and regardless of the surface you choose. Now, whether it's applicable or not, that's a different question. Whether it's plausible or feasible to apply or easy to apply, that's a different question. Whether it's true or false, it's always true. Okay? At least in the context of what we're applying. Okay. So, I'm going to continue an example I started last Thursday, or last time, I should say, and then continue to go from there. So, it's a spherical shell. And then I will do a solid charged sphere, and then or ball, and then we will do a line of charge and a sheet of charge. You already know the answers to them, but we're going to apply Gauss's law to them. So spherical shell. So what is the electric field everywhere? On a spherical shell. So what does a shell mean? A spherical shell? How would you describe a spherical shell to someone?
Like a basketball.
It's like a basketball, yeah. The only charge is only in the surface, only on the material, right? Which is on the surface. So here is a spherical shell. I would assume it's positively charged, although you can assume negatively charged. All it does is reverse the electric field line. So always start with pluses, and then you can always put a minus sign in front of everything. So this is a spherical shell, and it has a radius r. And in other words, the charge is just on the surface here. Okay, that's where the charge is. What is in here? Is there anything here inside? No, it's empty. And so the only charge is here. It's like my tennis ball here. And it's, imagine the charge is only on the surface. Inside is just empty. Okay? There's nothing. Okay, sounds good. And of course I drew just a side view, but it's a sphere. It's a spherical shell. Okay, it's a whole sphere. Now the question is, what's the electric field outside? And what's the electric field inside? Outside means r is greater than, little r is greater than capital R. Inside means little r is less than capital R. So I'll start with the outside. So it's uniformly charged. With total charge Q. So the total charge on this spherical shell is capital Q. That's the total charge. Okay? And the question is, what is the electric field here at R greater than R? So case one, outside, R outside. R is greater than the capital R. Okay. What's the electric field on the outside? Anywhere outside of the box. So Gauss's law says you draw a Gaussian surface, you draw some imaginary surface, and you're free to draw any surface you like. Now you can draw a surface where it's not useful, and you can draw a surface where Gauss's law is useful. So you have to take advantage of the symmetry. So what is something similar, or that imitates or emulates the symmetry of this spherical shell?
Point charge?
No?
Point charge?
A circle? You said the what?
No, that's wrong.
Okay. So some kind of a shell, some kind of a sphere. Yeah. A spherical symmetry. We have spherical symmetry here, so we would draw a sphere around it. So by a sphere, I mean draw something like that looks like this, and we will see why a sphere it works best. Okay. See in a second. So now, as long as you're at the same distance away from the center, you expect the electric field to be equal or different?
Equal.
Equal. Yeah. As long as because the sphere, it's the charge here is spherically symmetric, so I expect if I'm the same distance away, if I'm here versus here versus here versus here, or versus anywhere on this sphere, the electric field would be the same. We'd have constant value over the surface of this Gaussian sphere. The electric field would have what kind of value? Constant or different?
Constant.
Constant, good. Next, in what direction should the electric field point? Should it point, let's give two cases, or three cases. This is positively charged, so you expect the electric field to be away. So would it be this way? This way? Would it be 1, 2, or 3? Which one? 2. Yeah. So why should it bend one way versus the other? It's due to symmetry again. It's away. So I expect my electric field to point in this direction. So the electric field here will point in that direction. The electric field here will point in this direction. So the electric field here will point in this direction. So it's always away. Okay? Okay, that's good. Next, in what direction does the area point? What did we say the area?
Same way.
Always points away from the closed surface. So this is a surface, imagine it looks like this. An analogy I heard, and I like it, you know the animal hedgehog that has like spines going up? Okay, so it's like a hedgehog, it points in that direction. So, so just think of, that's DA. So DA points this way. DA here points away, so that direction. So DA, and this is E. Now you apply Gauss's law. You're ready to apply it. You found a surface over which the electric field is constant, and it points in the same direction as the area. So that's a lot of symmetry, and that will make our integral very easy. So let's do it. So we will write Gauss's law, the electric field dotted with the area over a closed surface is equal to the charge within that surface over epsilon naught. So let's look at the right-hand side first. My Gaussian surface, imagine this is your plastic bag or something, it's circular or spherical, and how much charge is enclosed within your big plastic bag or your Gaussian surface?
Inside is 0.
Inside it. How much charge do you have within?
Q?
It's Q, yeah. You have enclosed this entire sphere within your Gaussian surface, yeah. So
just the surface is Q, right?
yeah, the charge on the surface is Q, yeah. Yeah. So let's say I have charge Q here, right? Here's my Gaussian surface. My hands are not that big, but if I imagine I enclose it. So how much charge is enclosed in my hands?
Q.
Well, Q. I enclosed the whole thing, yeah. So Q. inside this surface is actually just Q over epsilon naught, whatever Q is on that shell. Now let's look at the left-hand side. First, E dot dA. These two vectors are parallel to each other. What's the dot product of two vectors that are parallel?
0.
If they're perpendicular, it would be 0.
Oh, 1.
Yeah, just if I have two vectors that are parallel, if I have A dot B, then their dot product is the magnitude of A times the magnitude of B times the cosine of the angle, right?
Yes.
Now, if they are parallel, theta is 0, so cosine of 0 is 1. So it's just A times B. So that's already a good thing. The vector signs went away. So it's just no longer vectors, I'm dealing with magnitudes. That's already a good simplification. See, that's why you want to choose your surface where the electric field is parallel to the area or perpendicular to it, one of them. So in this case, parallel works well. You can see probably why perpendicular will also work. Perpendicular, the dot product will be 0, right? So you either want something with no, you don't want any vector sign. Now next, here's the other simplification why we chose the sphere. Because the electric field is constant over that sphere. So E can be pulled out. So that's that. Now next, what's the integral of dA?
A.
It's A. And what's A? The area of the whole sphere, right? The surface area of the sphere. What's the surface area of a sphere?
4 pi.
4 pi E times 4 pi. Is it little r or capital R squared? Which
Capital
sphere
R.
are we talking about?
Capital R.
Okay, I heard capital and I heard little.
It's definitely not it.
Our electric field is on what sphere?
It's on the upper one.
On the yeah, so little r. It's on the outer sphere. That's where we're calculating the E field. So it's on the sphere that encloses the shell. So it's actually little r squared equals to Q over epsilon naught, and therefore the electric field is Q over 4 pi epsilon naught, and then r squared here. Right? You divide both sides by 4 pi r squared. So that's it. That's the electric field outside of the spherical shell. That's the electric field outside of this spherical shell. Any points in the radial direction. If you want to write it in vector sign, you put a vector here and you put r hat. Gauss's law enabled us to calculate the magnitude. The direction was determined from the symmetry, and we're done. Now what's the, I think I did this last time, but I kind of rushed it at the end. I want to do the electric field inside the spherical shell. Inside the spherical shell. Now, I don't want to gloss over the arguments. I want to be a little detailed on it. So here is the electric field inside of the spherical shell. I'm going to redraw my spherical shell. Here it is. This is the spherical shell. It has radius r, right? That's where the charge is. So this shell. Now I want to know what the electric field is inside. So meaning when little r, so inside, case 2, inside, r is less than r. R is less than r. So what's the electric field inside this shell? Okay. So once we're inside, here, so let's say if I'm here versus here versus here, as long as I'm a distance r away, from the center, what do I expect the electric field, what kind of value to have, should it have? Constant or changing?
Constant.
It should be constant by symmetry. There is no reason why the electric field here should be stronger than here, or should be stronger than here. Right? Everything is symmetric, so you should have constant field as long as you're on the surface of this sphere. So draw your Gaussian surface. This is, again, the real spherical shell. This is your ball or spherical shell. This is just the some kind of a surface that you drew. Okay? Now, so the radius is r. So I'm going to write down my Gauss's law first, and then we'll go from there. Gauss's law says the electric flux over a closed surface, so that's E dot dA, is equal to the charge that you enclose within your surface divided by epsilon naught. Okay, this step here is which law? Gauss's law. This is Gauss's law. Now, so here's my, I determined that the electric field will have constant value. In what direction, if I have an electric field, in what direction would it be expected to point?
Inward?
Either inward, or you might argue outward, right? Inward or outward, okay? So which is it? Well, let's just say it's either inward or outward. I don't really care, as you will see in a second why. So it could be inward, it could be inward, it could be outward, okay? That's fine, either one. Now, in what direction would the area point, though, of this Gaussian surface?
Offset. Outward.
Outward. Area is always away from the closed surface. So dA points that way, and the electric field, they said either parallel to the area or anti-parallel, right? Okay? So that's, are we okay with that? Okay. So if two vectors are parallel, their dot product is just, for example, if you have A dot B, then their dot product will just be AB, right? If they're parallel, if the angle is 0. If the angle is 180, if they're anti-parallel, then you would just get negative AB, right? So the dot product of E and dA will give me either plus or minus EDA. So I either get this, plus or minus E times dA, Q over epsilon naught. Either positive or negative, doesn't matter. And we will see in a second. Oh, I didn't say how much charge is enclosed. How much charge is within my surface?
0.
0, yeah. I mean, the charge is here. And I'm inside it now. And I have my hands like this, but I'm inside. Imagine the ball, the spherical shell is there. All the charge is on the surface, and you're here. So how much charge will you capture inside your surface?
0.
Yeah, you capture nothing. The charge is on here. It's not here. So there is no charge enclosed within your surface. So the right-hand side is 0. Okay, next. You might say already the electric field is equal to 0 because of this. Not true. The right-hand side being 0 doesn't mean what's inside the integral has to be 0. The integral is 0. So we have to argue further. The next argument is that since the electric field is constant, has a constant value, it can come out from the integral. So I would have plus or minus E dA equals 0. Now the area, the surface area of a sphere is 4 pi r squared, right? So this one is 4 pi r squared, and then I have plus or minus E equals to 0. Now you can conclude that E is 0. Now you can conclude that E is 0, because 4 pi r squared is not 0, and so it has to be this one. That's the 0. The electric field is 0 inside the shell. Yeah.
When we say like electric field is constant, that would be at the particular shell we're looking at, right? Because assuming like if there was, well, no, I guess it's on the outside. So like for the top problem, right? We assume E is constant because we're looking at a singular like radius. We're not looking at multiple different radius.
Yeah, we're a certain distance away.
Okay.
So the electric field would be this, and all you have to plug in here the distance away from the center.
Okay.
Yeah.
Why'd you say plus or minus E on the bottom and just E on the top?
Sure.
No, E on the top.
Sure.
Yeah.
Well, on the top there, I was able to conclude that the electric field has to point outward. On here, I'm not sure. I'm not sure whether the electric field should point inward or outward. I don't know.
Why on the top it has to point outward?
So let's see why on the bottom it may point inward or outward. So on the bottom here, let's say I have a plus charge, let's say I'm here, right? Just to, doesn't get cluttered. So let's say I'm here. I have pluses here that may produce an electric field that way. But I have other pluses here that also produce an electric field this way. And I have this plus charge producing electric field this way, but then I have another plus charge producing electric field that way. So are the ones on this side going to win, or this side going to win?
You don't know.
I don't know. It turns out they don't, none of them wins. It ends up being zero. On the other hand, when you're here, and I'm here, so if you're at this point, this charge will produce an electric field away, and this one will produce it away, and this one will produce it away, and the one that's closer will produce it away. So all of them are away, so I was able to conclude that. Okay. So that's a spherical shell. Now let's do a solid ball of charge. Solid ball means now you have a I have a bowling ball inside, but it was kind of heavy. I didn't want to pull it from the outside. So there is charge everywhere inside, right? So now let's do the solid ball of charge. And charge. Radius R and total charge capital Q. So here is a ball. This is the ball. Now imagine this ball is charged everywhere. So it's there are plus charges that say not just on the surface, but everywhere within the ball. It's uniformly charged, and the charge is everywhere. Does that make sense? So it's no longer a shell. A shell was empty from the inside. You only had the charge on the surface, on the skin of the thing. But this one, you have material everywhere. Yeah.
I was going to ask about, so because it's uniformly charged, does that mean it's in electrostatic equilibrium?
So far, yeah, everything is in electrostatic equilibrium.
Okay.
Yeah. So far, up to the next couple of charges,
Okay.
nothing moves. Yeah, yeah. We will get to currents; they will start to move, but nothing moves yet. Yeah. So clear?
Yeah.
That's the all right. So now let us go to start with the outside. Let's start with the outside. So case one. Start with the outside because it's easier. Case one. Let's see. What should I do for case one? R is greater than capital R, right? R is greater than capital R. So we're here. So as long as I'm the same distance away from the center, again, what can I conclude about the electric field? It's constant. To be constant. Yeah, it has to be constant. So it has to be, so the field here, or here, or here, or here, as long as I am a distance R away from the center, the ball looks the same to me. Right? Whether I view this ball from this side, or I view it from this side, or from this side, or from this side, it looks exactly the same because it's spherically symmetric, uniformly distributed. So the electric field, I conclude, as long as I'm on the same distance away from the center, the electric field is the same. Distance, or not distance, direction of the field, what can I conclude?
Away.
Away, yeah, direction is away. Electric field is away. Again, if you want to do negative, it will be inward. But why do negative? Just deal with positive and then just invert your electric field. Now dA is always in what direction? Away from the closed surface, right? So dA in orange here, dA, and the electric field is up. So they point in what direction? Parallel to each other. So we're ready. We apply Gauss's law. Gauss's law says, over a closed surface, E dot dA is equal to the charge that you enclose within your surface over epsilon naught. Let's look at the right hand side. There is the ball. My surface encloses the entire ball. So how much charge am I enclosing? All of the ball. Q, yeah. So Q. Left side. E dot dA, what did we say? E and dA are parallel, always, right? They're parallel. So E dot dA is?
E times
E
A.
times dA. Okay. E now can come out. And why can it come out?
Constant everywhere.
Because it's constant on the surface. You see, those are the two things you want. You want them to be parallel, or maybe perpendicular. We'll do a perpendicular a little bit later. But for now, let's say you want them parallel and the field to be constant over that patch or that surface. So E now can come out. dA, U over epsilon naught. And what's the integral of dA over a closed
A.
surface? Just A. And so E times A, but A for a surface is, of a sphere is
Pi r squared.
4, right? 4 pi r
squared.
Yeah. 4 pi r squared, Q over epsilon naught, and you'll get E is equal to 1 over 4 pi epsilon naught Q over r squared, right? This is for r greater than r. Notice this and this are the same. Whether it's a shell or a ball, it's the same. Because your surface, it's spherically symmetric and you're enclosing the same amount of charge. Right? Because after all, a ball is made of a shell on a shell and a shell and a shell and a shell and a shell. And so they produce the same amount. I mean, the total charge within all those shells is Q. Okay, now inside the ball is a little work, not hard, but some work. We have to do some work. Inside the ball. So let's go inside the ball, case 2. R is less than R. So let's make our ball now bigger. Make it bigger so that we can go inside it. So this is the same ball, right? So let me draw the pluses in orange. Okay, that's enough, right? Okay, that's good. So the charge is inside, is everywhere inside. So now I would like to know, what is the electric field inside the ball? Well, what kind of surface should I draw?
Circle.
A ball, again, yeah, or a
sphere,
circle, a sphere, yeah. So draw a Gaussian surface that has the shape of a sphere. And so the Gaussian surface looks like this. So again, this is the ball. That's R. That's the ball. Now this is little r. Right? This is my Gaussian surface. Now, so in what direction will the field be? Now we should know, actually.
Outwards.
It has to be outward. So let's see, if somebody want to tell me, earlier for a shell I wasn't able to determine, but now I can conclusively tell you it's outward. Why?
Because positive they always point out. Because
It's
they're
positive,
positive,
so it has to go out, but I have positives here. Maybe they will produce an inward and kind of make it inconclusive. Why do I ignore those?
Because they're not inside your.
They're not inside? You see this? That's like a shell. What's the electric field due to the outside shell? Zero. The shell contributes nothing to the field inside itself. So any field here is due to the charge enclosed within this sphere. So the electric field is actually outward, definitely. Yeah. The electric field is this way. But it is, I mean, it's this way here, and it's this way here, and it's that way here, right? That's the electric field. dA, of course, is away from the surface, and dA is this way. So I have this. Gauss's law, E dot dA, dA is equal to Q enclosed over epsilon naught. We actually have to do some work now to find what Q enclosed is. So we will do that a little bit. But let's look at the left side. E and dA are what? Parallel to each other, right? So E dot dA is
E times dA.
just E times dA. E dA. And then I have this. And I will keep this blank for a moment. Let me keep working on the left side. E is constant over the surface of that Gaussian surface. So move it out. So you have E. And then dA. And then dA integral is what?
4 pi r squared.
4 pi r squared. And now we have to face this right hand side. Now how much charge is enclosed within that surface? Not Q, not the entire charge, right? I'm enclosing only part of the charge, right? Only this part. This much charge I have inside my surface. This is excluded. So how do I figure how much charge is within my volume here?
The point charge thing?
Huh?
It's like,
I have many charges.
yeah, but it's all on the center.
By ratio.
By ratio,
Small
yeah.
L over zero.
So first I calculate the charge density, how much charge I have per unit of volume. And then if I multiply the charge density, the charge per unit of volume by the volume of my sphere, then I can find out how much charge I am enclosing. Okay? Just like if you have, for example, iron has a density of, let's say, I forget, about 8,000 kilograms per cubic meter, 8,000 kilograms per cubic meter. So if you have a cubic meter, that's 8,000 kilograms. But what if I don't have a cubic meter, part of a cubic meter? If I have half a cubic meter, then I will enclose within that half cubic meter 4,000, right? So it has to be proportional to the volume. So what I'm going to say then is this. The Q inside is the, let's do it here. I know that the charge density is charge per volume. The total charge we have is Q, and the volume is 4/3 pi r cubed. That's how the charge is distributed throughout my uniformly charged sphere. That's how the charge is distributed. So the charge within my sphere of radius little r, not radius capital R, the charge within the little r will be this. It will be rho times the volume. Times the volume. So it would be rho is Q over 4/3 pi r cubed times the volume. What's the volume of my Gaussian sphere?
4 pi r cubed.
4/3 pi r cubed, right? 4/3 pi little r cubed. Little r cubed. So the 4/3 in pi, so Qn, it would be Q, and then r cubed over capital R cubed. Capital R. Because now if my Gaussian surface has the same radius as the sphere, then I will enclose the total charge of Q. I will enclose the whole charge. If it's less, then it would be less. I would enclose less. Okay? So that is Q. So in fact, then Qn will just be this. Q, the total charge of the sphere, and then R cubed over R over capital R cubed. So that's what I'm going to write over there. Can I put the board down? Did everybody get this one?
Yeah.
Need a moment? Give you a second. yeah.
So this is just really a ratio of volumes, but since it's a bunch of concentric spheres, the other units cancel out, and it's only depending on the radius.
The units would be units of charge, right?
Oh, I meant like, so, since it's, oh wait, no, never mind. Never mind, I figured it out.
Okay.
And
Yeah.
so for the inside, why do the positives cancel out? Is it just due to the symmetry? For the inside of the sphere?
Inside of it, you mean due to the shell from the outside?
Yeah,
Yeah, those do not play a role.
okay.
I'll come back to that maybe in a moment.
Okay.
Yeah. But for now, I'm going to copy this. That's that's what I need from this board, is Q R cubed over capital R cubed for this Q inside. That's what I need. So it is, Q little r cubed over capital R cubed, right? Yes. Let's write it one more time. And one more time. Q. So,
Isn't it over epsilon?
and over epsilon naught. Yes, I forget the epsilon naught. Epsilon naught. Otherwise, the units are not going to be right. So next, divide everything by r squared. So you get E would be 1 over 4 pi epsilon naught, or Q over 4 pi epsilon naught, Q over 4 pi epsilon naught. And then you have capital R cubed. And what happens when you divide r cubed by r squared? End up with just r. And that's just r. So this formula is for the electric field less than r. Do they match with each other?
No.
So let's see. So this one applies when r is greater than capital R, and this one applies when r is less than capital R. Let's try to graph it, plot it, and see what happens. I'm going to plot both. So here it is. Here is R. Here is capital R. And here is the electric field. Starting with R less than R. Starting with little r less than capital R. I'm still okay with the time. So which formula should I use to plot here? This one or this one?
The one on the right.
The one on the right, this one. So now what does this one say? If little r is 0, what's the electric field if little r is 0? 0. So it starts at 0. And then it says it grows linearly with r. It's proportional to r. Little r. So it grows linearly. It goes like this. Okay. Now what's the value when little r is equal to capital R? At this point.
Q over 5 pi.
Q over 4 pi epsilon naught capital R squared, right?
Oh, yeah.
Because you have capital R over capital R cubed, you have capital R squared. So you have here Q